finish off this brief look at probability distributions, we're going to look at this idea of statistical inference. So to infer things. Now that's the whole point of gathering the data and using stats, is we then go and infer things, make predictions and that sort of thing. We use that data. When we're inferring what we do, we've got our data, we've pulled out our sample. Often we use samples rather than the whole population. It's not always practical to survey everybody. But then from that sample we've drawn, we then can make these predictions about the whole population. So what is sampling exactly? It's simply a selection of, well, I've called them elements. Just think of a set of objects. So a selection of them. Could be a finite population. There might be an infinite number of things in the set that you're pulling things out from. But why do it is the question. Okay, speed. It's going to be quicker to pull out a sample than try and get every piece of data. Cheaper. If you're paying someone to go out and, can you conduct a survey for me? If they're going to have to ask every single person, it's going to cost you more money. But actually, this is the interesting thing. It's more accurate than going the whole population, because errors happen. And if you're going to go large samples, or even the whole population for that matter, the more that you ask for, the more chance of a mistake happening. So accuracy, actually, when your samples are smaller, you can't have them too small, of course, otherwise you don't get good results. Necessity. Yes, the example I got here. You can't always test for quality on every item if you're then going to destroy the item by testing it. And the example I put there is matches. So you're in a match factory, you want to see, you've just produced these matches, see if they're any good. No worries, I'll go strike the match. And if you do that to every match, they all work, but now they're no good to you because you've struck the match. So it doesn't make sense. So how should you go and get these samples? Okay. Always randomly. So a sample is going to be random when in that population every element has an equal chance of being picked. If some have got more chance than another of being picked, then you don't really have a true random sample. You're more likely to grab that person than this person. There can't be any bias or predictability involved. When you are random sampling, it's not necessarily going to get you a complete cross-section of the population. Ideally, you would like your sample to match the whole population. So if in the population there was, 20% left-handed people, you'd like 20% left-handed people in your sample. But that's not always going to work. So you don't necessarily get a cross-section when you sample. Okay, terminology. They're just technical things. But if you are going to collect your data on the whole population, we don't call it a survey, we call it a census. When you're just gathering a sample, that's when you call it a survey. And there's a subtle difference in the notation we use as well. So as we've been doing now is just PX for probability of X. Now technically that's what you use when you've got a population. For a sample we don't call it probability anymore, we call it relative frequency rather than probability. They're the same thing, but they're just different words we use. The symbol we used for average or expected value. Mu is when we're talking about the population. When it's a sample, we tend to use X with a bar over the top. That's the symbol for expected notation or average. And variance also is different. Sigma squared when we're talking about the population. S squared when we're talking about the sample. So you might see these symbols used in different times and you think, hang on, why are they changing them? And this is why. We're talking about a population or we're talking about a sample. But what should happen as the number in your sample approaches infinity, so approaching gathering every piece of information, you should find that the X bar approaches the mu, if you like. So the average of the sample should approach the average of the population. And same with the variance. Same with the probability as well. The relative frequency should start approaching the theoretical probability, for a different word. Let's just have a look at this one then. So we're going to roll 2 dice. We're going to use theoretical probability to calculate the expected value and the variance for the population. So theoretical probability is when we don't actually do it, we just use the theory behind it. And so we would assume that a 1 in 36 chance of getting a 2 and things like that. But anyway, we conducted an experiment, and here it is. I did a simulation on a computer to save ourselves some time. Now, this is not the actual rolling of the dice. This is the theoretical one that should happen. So a 0.0278 chance of rolling a double one, and so on as we go along. I've then created the xpx and the x squared px row for that information. The expected value is 7, you will see. And the variance is 5.83, well, repeater. So 5.833333, and so on. That means the deviation, or standard deviation, is 2.4152 approximately. If I was to graph it, it's a beautiful symmetric graph. There it is. So in theory, that's what should happen. What happens in reality? Okay, so we're going to roll a pair of dice, 50, then 100, then 500, then 1,000 times to compare these samples with the population. Now, of course, I didn't actually roll the dice. Again, I got the spreadsheet to do the work for me, but made it a random number generator so I could simulate the random falling of the dice. And this is what happened. When I produced 50 results, you can see what ended up happening. Now, the top 3 rows are the theoretical one that I had before. So down below now it's relative frequency and so on, what happened when I did the sampling. And you can see that's slightly different to what actually happened. The expected value of my experiment with 50 was 6.42, and not quite 7. There's the deviation, 0.58. The variance for that one was 5.8036. If we put both of those on the graph, so the diamond one there was the theoretical, the asterisks are what the experiment did. As you say, the bigger n, it should get closer to being that. And you can see, well, look, the one right at the top there, a long way off, and so on. I mean, I could redo that experiment and I'd get different results, because it's all just random. Well, 100 times, so let's increase it. 100 times, here we go. What happened? 7.16, got closer to 7 that time. And there's our variance. What happens with that graph? Here we go. Okay, they're coming in. It's getting a bit tighter, closer to the actual probabilities. Do it 500 times. When I did it 500 times, 6.86. And variance, let's have a look at that graph. There we go. Not too bad. And 1,000 times. Did it 1,000 times. 7.042. Getting very close to 7. So it's out by 0.042. And there's my variance. And wow, 1,000 times, and now it's really getting close. And obviously I kept doing more and doing more and doing more. I'd expect that to really start fitting well. Look, I haven't said a lot of questions out of this one. There is a lot of experimental stuff, and if you want to use spreadsheets, if you understand spreadsheets and that, well, I'll maybe have a go at 4 of them, see how you go with it. It's this idea of doing samples and let's see how it compares to the actual theoretical probability and what have you.